So,
Hey.
I often think that I'm late, but I guess a lot of people are also late for Saturday voluntary meetings.
Well, maybe their previous stuff gets long, goes longer a little bit. So
The previous, what?
yeah, I was in another class, and that actually finished 2 minutes early, so I got here on time. But sometimes it's over.
Another class before this, another commitment?
Yeah.
Oh my gosh.
Yeah. I guess I bit off a little bit more than I should have. But, these classes don't happen on my timeline, right? It happens when it happens.
Yeah.
So I kind of get on the train or.
Yeah, what is that? So this, like, is it a study group in the same sense, or is there more commitments?
That's also a study group, and that's been going for a while. It's the PieTorch study group.
I see. Oh, that's always. I have a group that I meet with on Tuesday nights.
Okay.
We meet Fast AI group from a year ago, and we still just meet for fun.
Okay.
And PieTorch, that's a great tool. I'm telling you, it seems to go deeper and deeper and deeper the more you look. As a matter of fact, I was just troubleshooting something, and sure enough, I saw Sylvain's name pop up. He is on. He will respond to everything within minutes, it seems. You know Sylvain Guger?
You mean the Fast AI guy?
Well, he's actually all over PieTorch too. I used to, exactly. He's the same guy that was, I think, working with Jeremy on Fast AI. But of course, Fast AI is just kind of a wrapper above PieTorch. So I saw him responding to a question in some PieTorch forum that was just like a few weeks old. But he's still so just helpful as a resource. That stuff is complicated, of course, as we've discussed. So complicated that I'm not sure I quite get the whole picture so far. Maybe the easy stuff. I'm sorry, I'm chewing on a protein bar. Like I went ahead and started to plow through Colab, I guess 2 now. And I really haven't done much with neural networks, but I kind of have the idea that you have to kind of put your layers together end to end. And what I didn't understand was, where does the adjacency matrix make its way into the actual calculations on just the very first step?
So that's for the GCN conf layer. If you look on the PieTorch geometric definition of the GCN conf, you can see where the adjacency matrix come in. So it's part of the how it's set up. So you need both the X info and the adjacency matrix.
Yeah. In the actual forward function, you use the adjacency matrix as part of the operation?
Yeah, so like in Colab 2, you're basically your GCN network consists of like the conf layers and the other batch norms value, etc. And the conf layer is the GCN conf from PieTorch geometric, and then that's where it's used. So because your forward function, you pass the stuff through the whole set of layers. So you only need to use it for the conf layer, like the actual conf operation.
Yeah. Is it actually a parameter in the, I'm looking for my forward function. Okay. I thought you only pass in X. Do you actually pass in X and adjacency underscore T separately as another parameter?
Yeah.
Huh, okay. Maybe I didn't, it looks like the GCN conf model has input channels, output channels, And that's all. Oh, maybe that's just the option.
No, if you go on, so if you're reading the docs, the class GCN conf, that's it, how you initialize it. It's not how you
Oh, thank you.
how you actually, like, if you look at the bottom, like if you look on the bottom, and if you look at the end of the section on the docs, it says forward is x torch.tensor edge index edge weight, and returns the torch.tensor.
Okay. Got it. I didn't actually.
Okay, so that X is like concatenation of tensor and the adjacency matrix, is it? In the forward function.
No, X is just like the node stuff. Then you need to pass in the adjacency matrix separately.
Oh, okay, sorry, yeah. So there's a big comma in between. Yeah. So X is the node, and the edge index is that adjacency matrix. Correct?
X is the data set, which includes
X
a
is
lot
the
of
data.
information. But adjacency is a separate parameter.
Okay.
Yeah. Okay,
So-
that makes sense. And it's symmetric. It just kind of comes out, I guess, as the edge list.
So what is this like edge index? Like I haven't done this, the collab 2, but still, like as we've just taking part in the discussion. So what is that edge index? Is it one index, or it's a list of all the indices and which are basically represented in adjacency matrix?
That's what the edge index is basically just the adjacency matrix.
Yeah. So like okay. Okay.
And those data sets are actually a little bit complicated, but they're all well documented. Within one data set, it actually has several components. It has the node information, the features information. That was actually part of the collab, was to kind of tease those out, how to get, like the number of edges is just one of the two shape parameters, right? And if it's a undirected, it's divided by 2 even. It's just that simple.
So my question is how is the edge index represented? That matrix is represented here when we are putting the input in the forward function. We have this edge index parameter. What is the data type? What we are passing there? How we are passing that adjacency matrix? It's a list of lists. Is it a like NumPy array or something like that?
It's
Or
a
tensor, right?
yes, because the whole thing needs to be in PieTorch tensors.
Oh, understood. So yeah, it's basically a tensor of all the pairs. Am I correct in understanding that?
Correct. I'm just scrolling back through the example at the top.
So Dave, if you are like opened it already, can you share the screen so that we also know?
Very good.
Because I haven't started that yet, so maybe it will help me to
My
get it.
example is, mine is always kind of half broken, but let's see if I can figure out which desktop. Okay, so you're seeing probably my big desktop. Let me move that.
I don't think I'm sharing yet.
Oh,
yep.
Sorry. Oh, I gotta select it and then press share. Okay, so.
Yep, can see now.
Everything gets in the way. All right, so yeah, here we are at the beginning. I did notice that I had to uninstall a few things in order to get this to work.
I
So
think
I'm
not sharing the correct thing.
You're sharing something fidelity one, but yeah.
Oh, it's probably something very private. So, I have
well, it's all right. You have logged out, so.
Okay, let me open some like Colab to visit if I can.
Okay, that looks right.
Yeah. Now we can see.
So I had to uninstall these two in order to get the versions proper. It was complaining that PieTorch was compiled under something 11, yet the Torch scatter was compiled under something different. So I just uninstalled it and then told it to install again, using specifically the versions that we were hoping to be consistent. And that actually worked. So I posted that in the chat too.
Yeah, you also posted that.
Yeah, without that, the game was over. I couldn't proceed. And then of course, it's just pretty simple following directions. You just, of course, print out what it does. And the data set itself is just one of several data sets that come into this guy. Specifically, it's this data set. And it, by default, spits out the number of nodes, maybe? No, actually the number of graphs.
Oh, the graphs.
So that's what I'm getting. I don't realize that each data set is multiple graphs. I think about graphs being one big thing, but indeed, this is a data set that has multiple graphs. Okay.
So the TU data set. So there's a different. So it's not always a lot of graphs. Some of the data sets are just like one graph, and then you classify the nodes. So it really depends on like which problem you're working on, because like in the lectures you probably should have seen that you have got three like GNN and problems. One is node classification,
Right.
edge prediction, and graph classification. So like if it's a graph classification problem, then it will have like multiple graphs in the data set. But there are some other ones where, say for example, you're doing node prediction where you might only have like one graph.
I see. TU data set is a set of graphs, a set of data sets. Actually, I changed browsers. Did the presentation change?
Oh, we can still see it.
Are you seeing PieTorch geometric?
Yeah.
Yeah.
Okay, I just want to make sure that you know how when you share, you can share an application or an entire screen, and I only share the application, but it's an application browser that I have everything open in. Okay, so the TU data set is one of these that has in it multiple, I forget where it is in here, but of course it's not alphabetized. Like what? There it is.
Yeah.
So this has a bunch of data sets. Some of them have only one. Okay, I think I understand that. Okay, so this was just kind of an exercise in how to pull out the number of classes, and it actually is a feature that comes with the data set. So that was an easy one.
So if we are looking to one data set, and if there are a number of graphs in that, does it mean that all those graphs are of this, like they pertain to same topic? Is that understanding correct, or there can be different graphs in a single data set too? Maybe like a combination of karate club and football club.
Yes, that's coming up actually. So the number of classes, I think, is of course one per data set.
Okay.
And then the actual classes themselves is coming up next. Number of features for the nodes is also given as a standard object in the data set that just gets spit out with this selector, and out it comes. So this has 6 different classes. I guess for the whole data set, those are graph classes. Is that how that works? Graph classes, not node classes, or is what does that mean? I think it's the total number of different classes that will, each of the 600 will be put into one of 6 classes. Is that right? Or ideally, they're exclusive. Maybe not exclusive. That's another whole question, but this is classes of graphs in the data set, right?
Okay.
And this is features of nodes.
Individual nodes, like intrinsic feature of that specific one node.
Yep, a given node has 3 features. I don't know what they are, but we'll find out. So the question is, in this next question, for this particular graph, specified by IDX, that's in this data set, tell me what is the label of that one. And that one is a little trickier because you have to, well, actually, it's almost as easy. Indexing into the data set for the given graph is simple indexing into the data set with the parameter pulled in. And then the .y is the actual label for that graph in that data set. So .y is the y, you know,
that is for the specific graph.
Yep. And it comes out as a tensor that you have to turn into a integer.
Okay.
If it's specified as integer, which it was in this case.
So total number of graphs in that is the data set is 6, like what you have figured out in
600.
So total 600, but then what is that 6th number? Okay, total
That's
number
the number of different different classes. And integers 1 through 6, I presume, but that's not guaranteed, I don't think. It just happens to be in this case. I think I went and pulled another one out.
With 100 IDX.
100 is label 4. So this, if I chose a different index, this might be label 2. I assume it's 0 through 5, but I don't know if that's
correct. Total 6 classes. Yeah, I think I'll try to figure that out.
Okay. Edges, same kind of thing. It's fairly easy. It actually has the edge index, and the shape of that, the second parameter of that would be the number of edges. The first parameter is what? The number of, hold on. So number of edges. What would be shape sub-0 conceptually?
There's also you can just say graph.num edges. There's a function in the graph itself.
I didn't think that was available for some reason. I just saw an example, I think that showed that wasn't an actual parameter, but I guess you're saying it is. And let me run before. Let's get this going while I'm talking, so I can do that. Okay, so it's fine. Then runtime run before that. I'll just run through and reload all that. Okay, I think this is just kind of calisthenics, trying to get handy with what we're dealing with, which was great. I appreciate this level of almost tutorial. Then things get a little more complicated, I guess. We're getting into the torch geometric. I think this was also just kind of an example of how to load a graph. Just printing out something about the graph, which tells you then all the details, at least the shape of the nodes. 128 features. This has this many classes. Is that right? Or is that the number of classes?
No, neither. So the first one is the number of instances.
Yeah. Okay.
That you need to classify, and the second one just means that for each instance that you classify, there's only one label.
Okay, got it. One label.
So like if you need the number of classes, then it'll be the number of unique labels in Y.
Right. Which would come out with, as we learned before, data set num Okay, so I should be able to. Okay, so I should be able to. If you said, okay, what are the number of edges? It should be num edges, right? Oh, it's got to download the graph. Okay, that's fine. Yep, 116. Okay, so the adjacency matrix has, of course, a matrix of this dimension. Adjacencies are nodes to nodes, right? Okay, got it. What is edges? So why does this number disagree?
I think that's like, because it's a sparse matrix, it's probably something related to that, the N and Z thing.
Got it. Got it. Not every node connects to every other node or something like that. Edges. Okay. Anyway, we're just kind of getting used to using the tooling. Pulling out the number of features is, I thought, the second parameter of the shape of X, which is that right?
There's also num feature.
Well,
Isn't there num features? Yeah, data.num features.
let's just see. You're saying that it's an entire. Yep, there it is. That doesn't mean it's necessarily there. I've learned sometimes the type ahead seems to get confused, but yep. Okay, so those are equivalent. Great. All right, so loading Torch geometric, and of course pulling in GCN conv seems to work fine. Okay, now things get quite interesting. Confirms that the CUDA device is available, prints it out. And now we're talking about the training. So there's a function within this data set that lets you pull out the indexes for training. That's fine. And then we print them out that it's 90,000 elements. Now, this is, to me, is confusing. Why? What is this second little piece here? And this,
the piece on the right is the final layer, and then the one layer, the stuff on the left is one. You can think of it as one unit. Like one unit, and then you repeat the unit on the left multiple times. So a bit like
you do?
Like for example, like in one of the CNN's architectures, that's quite common, like ResNets and whatever, you tend to have like multiple that form one bigger layer, and then you repeat that thing.
I was assuming that these were multiple. There was multiple versions of this and multiple versions of this. One of these, but you're saying that this actually repeats?
Yes. It's the four things that repeat together, not individual bits.
And when you specify, when you declare that one of your networks is in this list of things, it only has one thing in the list of convolutions, but it has this number of layers. So I may have done this completely wrong.
No. You kind of need to so the first GCN conf will have input channels as input dimension and output channels as a hidden dimension. And then for the next
really got it.
Yes, and then the next ones will have
output dimension is here.
Yeah, so the ones in the middle have to have both in and out channels as hidden dim, and then the last one will have input as hidden dim and output as output dim.
Okay, and do I specify multiple types in this list? For like, do I put the batch norm in This
No.
list?
No. So
Mhm.
like your thing, you don't, because it's just a list. You can think of it as a list, so you can iterate through it later. So you don't need like bash norms and whatever in it, but it's just more kind of a convenient way of holding the list of conflict of layers. And I think there are certain guarantees with if you use an n.module list, that's a bit nicer than just a list, but you can think of it as just a normal Python list.
Okay. So it still has the number of layers. Output of the hidden.
You need to remove the for I and range num layers.
Oh, I thought that's how you got it to have the number of layers, but that's not true.
No, it's you, because you need like approximately how many you need, say for example, you need 5 GCN conf layers, then you can't have each one have input dim and out panels at dim, right? Because the things will not match.
Yeah.
Input dim only.
When you think 5 units, it means like the whole left block 5 times, correct? The GN,
Yes.
CN conf to drop out.
Well, not exactly. So the last one is GCN conf and softmax.
Oh
but,
no, what I'm saying, you meant, okay, so 4 times this left block plus 1 output GCN call to softmax.
Yeah.
This is
but,
the number.
But it really depends on how you want to define your num layers, obviously.
No,
so
I think when you said 5, I was just using that as an example to basically understand which all like layers are we repeating here.
This is num layers, the number of cycles through this thing.
Okay.
Through the first part. Okay. And then that means there has to be a loop. In my forward, I have to do a loop that I'm not doing.
No, it's you specified that in the module list definition.
Actually in the list? Or in?
Yeah.
Okay.
Should I share my screen? It might be
that's what I was trying to get to the point. This is where I was having trouble, and so I so appreciate that we're doing this, and I hope it's not going to impinge too much on our time for many other chapters that I haven't looked at. Now that makes perfect sense. It was not making sense to me when I was trying to logically compare my logic to the picture.
Yeah, so this is my collab too. Let me find it. Yeah, so here, so I basically defined the module list as you start off with just one. The first one, which is input channels, is the input dimension, and the output channel is the hidden dim. And then you loop through the 1 to number layers. Then you say kind of the conf module list. Then you add in each one where the input and the output channels are the same with the hidden dim. And I also, at the same time, I also add the relevant thing to the bash norms list. I mean, you can separate the for loop out, but it's just it's the same. And then you for the final thing where it passes into the softmax, then you say hidden dimension for the input channels, and the output channels is the output dimension.
Got it. Where's your softmax?
So the softmax is here. You just define it as that.
Where is it part of the forward pass?
No, this is part of the init function. So you define everything here. And then when you do the forward, then you basically loop through. So I say like X is pass it to the conf, pass it for background, pass it to ReLU, drop out. And then finally, so I loop through all the one in the first left block. And then once I just done that, then either I return embeddings, in which case I just drop done. And then if not, then I pass it to the last conf layer. And then I can't get the softmax layer to work correctly in terms of shape. So I just return that, and then I use a different, because if you use cross entropy loss, you can just not worry about the last softmax layer. So that's what I've done.
Okay. That makes sense.
Let me see if there's somewhere. Yeah, so kind of I use cross entropy loss instead of the one that they gave, and then it works with
that will cross entropy loss will basically take care of the numbers that would have been filtered out with softmax.
Yeah,
okay.
And it's happier with the shape of my tensors.
Okay.
So like, yeah, that's a bit easier. And then
so your construction of the model in the init actually is constructing all the layers differently. That sounds good. I like that. That looks much better. Then your execution of forward is basically just executing each section, which is made more complicated by the init. Okay. Got it. That's wow. This stuff is just kind of magic how it all just kind of works together. Brilliant. Okay. Well, that's as far as I got. That was kind of the whole point. So, all right. I really didn't look at 7, 8, or 9, but I'll be glad to listen if people want to start reviewing and talking about that.
So mostly it was 8 and 9 were very theoretical. It talks about augmentation and how to add the intrinsic info and what are some of the issues there. For example, it's not able to understand the cycles when the graph networks are not able to understand the cycles between them. So those kind of stuff he talked about in 8. 9th I just finished in the 2 hours back, so I'm still yeah. So
augmentation, I do remember you in image processing, whatever we did with PieTorch and FastAI, augmentation was a very important aspect of kind of formatting the data in a way that made the problem function better. Is that also true in this exercise?
Yeah, so in the 8th list, what do you call lectures, he talks about why do we need augmentation, and basically tells the reason of their importance. So I guess it is so there is a table on 10th slide of 8. So where he talks about some of the issues like feature augmentation. Let me share that. This was the sort of just one of the just slides of that.
Instant. Okay, so one hot is an augmentation.
So let me give you a bit of context there. So when we are talking here, he gives the reason that just a second. Yeah. So right now here we are just looking at our neighbors. Then he wants to know. Then he wants to stress on the fact that we can add the features of the graph on the this individual nodes which can help us in some way. For example, if we have if we add just one to assign constant value to all nodes, so if we have that thing, then when we are collecting information from our surrounding graphs, that the total when we aggregate the total number of neighbors, that the output the whatever we are getting from the neighboring nodes will have this value as one as well, and so the total amount will tell us like what was the size, what are the total nodes that specific this A node has, and
Right.
further it will also have an influence of what its neighboring nodes, how many nodes the neighboring nodes had on the like maybe in like next step.
Right.
Yeah,
it's
so that is one of the things he talks about, and but the issue, yeah, sorry.
Is that augmentation? Is that kind of what to me, augmentation is doing something. Okay, so that's an aspect of augmentation, I guess.
Yeah, so basically we are trying to augment the what we are putting as input to the layers.
Okay.
So next, basically he talks, but right now we are not able to, we won't be able to distinguish between this A and, or maybe, so A has 3 nodes, okay, not A. So if I talk about B and if I talk about E, both of them have two neighbors. So right now in the first step, we won't be able to tell difference between them. So then he goes about like augmenting in them by the one hot vector nodes, so that we give some specific node values to each node, and based on that we do this one hot encoding. So that will help us in understanding and getting the information about the more granular structure of individual nodes. So which all node this A is connected to, and which all nodes this A is getting information from, and which all nodes that B is getting information from, and so on. Now he talks about what are the issues with that. So this is basically expressive or is medium. Like, yeah, we can learn from it, but then we cannot generalize it to new nodes. So if I get some new nodes here, sorry, we can generalize to new nodes. If I get some new nodes or a graph where I haven't seen some nodes which are not present in this graph, then I'll be able to assign them just one as one like value 1, and it will be done. So, but in this case, if some new nodes come, if there is some new node, we won't know like how to assign those values to it. So we cannot generalize it. And again, computational costs, and that it is comparatively lower, it is higher in terms of space as well as complexity in terms of calculations.
That's cool. Yeah. So the one hot node informs not of your immediate neighbor, but actually of other ones that are just one hop, but are expressed through that neighbor.
Yeah, so basically it tells you more about, so as it says, the expressive power here is higher because it gives you node specific information. It does not give you node specific information. It basically tells you the total number of nodes from which you are getting information from.
Lack of specificity. Okay.
Yeah. Yeah, totally. So now the reasons of feature augmentation, as I was talking about earlier, that like if you have this node V, it is connected to 2 other nodes. This V1 is also connected to 2 other nodes, but right now it is connected to a triangular cycle. It's a like 4 node cycle. But then this, if I go about the way our graph has been formulated till now, we don't have any idea. I mean, it won't be able to tell difference between these and these. So those kind of, how do we like go along solving those issues?
Okay. Wow, I see. There's ways to, like, I'm thinking of image processing where you augment, you do edge, you kind of amplify a pixel, you augment that pixel based on neighboring information to help the process of whatever it is you're trying to do. This is the same way. You're kind of amplifying or augmenting a feature on a node in order to make something else more expressive or work better.
Yeah, so I think the whole idea is to go about these 2 things. Like first is about getting the idea about the whole graph, as well as getting the idea about like node specific understanding with respect to the node in which we are interested. So those 2 things we are trying to address here. So No, so some other, he talks about some other things like node degree, etc., page rank centrality, just one line. So these are the features we talked about during the lecture too, and he says that those things can be used. Now, yeah, some new stuff here. So he talks about adding virtual edges and virtual nodes. So the idea there is to reduce the information distance between two nodes which are pretty far apart and basically have a very long walk between them. So in this case, for example, if we can like have a virtual edge between two nodes which are at two jump apart. So we can use that using a plus a square computation. And he gives an example of bipartite graphs. So for example, if just author is connected to all the papers, but if I have a connection between individual authors too, so I can understand that which are the two authors which have worked on a similar on a same paper, or which are two papers which have been authored by by a single author. So those kind of author and or like
That's what he means by
paper
author
connection.
author.
Sorry.
I know he's mentioned author before. I didn't know what that meant. Okay.
Yeah, so because this is a bipartite graph, and here each author is connected to either one or more papers, but right now there is no direct connection between authors. If I introduce some of the virtual connections between them, then that information can be easily accessed.
Mm-hmm.
And then adding some virtual nodes. So here we were adding a virtual edges, and here we are adding virtual nodes. Basically, what it does that it reduces the distance between the far nodes. So, for example, if I have this D and C, they have two distance, like D or maybe F. But then if I introduce a virtual node, both are basically connected to this virtual node, and they can share information between them. So he gives example of A and B.
Ooh, that sounds like
yeah. Sorry.
You have it doesn't seem sensible to just add edges that are completely fiction when
that is one of my question. Like, if it doesn't it change the whole structure of the graph if you are exactly trying to understand what that graph represents, if you start adding edges and nodes, and that is my question exactly.
How do you distinguish one edge from the one that you just made up, the real edge versus the other edge? But I do understand the author that, because you don't have any other way to make author, you just make it up. I mean,
so yeah, in further slides, I think where one of the places he talks about the like differentiation between edges, the edges which are used to calculate some stuff versus the edges which are just being used to pass a message. So I haven't like completely digested that. But it was mentioned further, I think in 8th or 9th, I'm not sure which chapter. Okay, so this I think he did like already. So new idea, randomly sample and nodes enabled from message parsing. Yeah, he talks about some of the nodes which have very high number of connections. In that case, how do we like the whole calculation become problematic? So we start choosing on each layer, we start choosing randomly some of the neighbors which pass information to them. But then the issue is that if there might be edges which might be having some so there might be connections which could be passing very much important information. In that case, if we are just ignoring those edges get ignored, then the information might not be readily available, which could be important. So the thing is, if in layer 1 we are using some specific sample, then in layer 2 we'll be using some different sample.
Good
so
idea.
In that way, it generalizes, sort of thing.
Yep.
So yeah, this is the example he gave. So if I have A which is connected to B, C, and D, and I just sample 2 of it, so I am sampling DA and BA. So that could be in first layer, but in the second pass we might be using maybe AC or AB. So if we start choosing them randomly, then over multiple layers, this issue is sorted out. So he gives an example of very high degree like nodes. For example, I think he mentioned on Twitter or something, Instagram, Kardashians has so many nodes. How do I know that? How do I calculate? If I start calculating, I can't do that. So I start sampling.
Right, but you wouldn't sample it with like anything specific like feature weight. You wouldn't have a deterministic sampling. You'd have it more random.
I guess so, but I think that will also have some weights while sampling. I'm not sure yet. So that
Like the-
that I think we'll get to know later.
Like
Sorry.
the function or the criteria for sampling would be very much a part of a possible problem or part of a very good approach, depending on what you're trying to get.
Yeah. So
I mean,
yeah.
also something you can tune hyperparameter, like how much you use the weights, but I think in the end you still need, so even if you weight the sampling by edge importance, you still need the randomness, because otherwise you just don't get the whole picture.
You begin to impose something about the problem, not about the solution, not about the problem.
So then he goes on about training and okay, input network.
Now we're getting into the heart of the matter. Yeah.
The harder part, yes. So yeah, so okay, what was the prediction head? I have forgotten. Okay, so
the prediction head is a bit like the example we were seeing earlier, where it's like the conf and the softmax. So that's just turning your embeddings and stuff into your actual, like if it's a classification, like what the labels, that sort of thing.
Layer.
Okay, so I guess so this tells you what exactly prediction heads are. There could be, I mean, it's specific to the task. Is that what you're saying, Wendy?
Yeah, and say like if how, like you'll kind of change according to like I'm not predicting 3 classes or 5 classes or yeah, that sort of thing.
So basically it will depend on what use case you're trying to solve. So if you want to solve some node specific or edge specific or basically graph level tasks. Okay, again, example like node specific prediction, edge specific prediction. Okay.
Well,
so
that kind of gets back to a question I had about this prediction head. So in the example that we went through on Colab, a lot of the architecture was done in the init, but could that have also have been done in the forward function or not?
You can do it in forward function. So, well, you can, like, because at the end of the day, you can, for example, use a more functional approach, but it's just, in some ways, it's a bit tidier if you define it in it, because like you can specify like various custom stuff, or you can do things like what I showed you, like where you just loop through all the layers that you need, rather than like if you put everything in forward, it's just a bit messy.
Yeah,
if you see,
forward should be very straightforward. Like it should just be do this, get the filter, be done. You know. Okay. Just kind of wondered because you're still in the model, you're still in the defining in the class the complexity or the actual architecture of your solution. Is this prediction head something a little different? Is that a separate section then? So the graph neural network square thing, is that where that would be like the init function, the actual definition of your architecture? And then the prediction head is something that you can even use for more customization? Oh, I see. No, it's focused on nodes, edges, or graph. Okay.
Yeah, so prediction basically talks about like what exactly your final target is. What do you want to do? So then he talks about this node level predictions and edge level predictions and graph level prediction. He gives some of the examples there.
Okay.
So, yeah. So.
Good.
So these are basically he talks about like what he has already talked about. How do you concatenate? How do you do and how do you get these things? So just jumping over them. Yeah. Some of the pooling thing he talks about that like some, yeah. So I think there is a direct. There was a, sorry, just a second. So he talks about some of the pooling architecture. Then how do you? So if you have a vector, then you either take mean, max, or sum. I think graph sage takes mean and GCN takes max, something like that. So further he talks about what is the issue of with each of them. I think in the ninth chapter, ninth lecture. And okay, so here this one, hierarchical pooling, where you take a sample of I mean a group subgraphs, and then you start pooling on that individual graph, like subgraphs, and then you keep hierarchically like pool those individual subgraphs together and further on till you till you basically end up pooling over whole graphs.
Right.
So
classic pooling mechanisms.
Yeah. So I mean, these are like basically the concept he talks about. He gives those examples. What are the issue with them? For example, if you take this one and these two things, if you take like average pooling, then and pass it through ReLU layer, it gives you simple these values. So both of them give 0. So you cannot basically differentiate between them.
Yep.
And you sum it up, then you can differentiate between them. But he also gives them the case where the sum has the problem. So in the end, like he talks about, like this hierarchical pooling helps you in like making sure that you are using the cluster level features also, and you are able to get those things in your final output too. So yeah, that's okay.
And so in that case, for pooling, you're using whatever features you want from each of the.
Yeah.
Okay.
So instead of basically pooling over everything at once, you pool across the clusters together, like those who are close, and then further down, like you do it in hierarchical manner. But then how do you identify the clusters? So he talks about that there you have two GNNs, GNN A and B, and you basically train them. So you use clustering assignments from GNN B to aggregate nodes embedding generated by A in A. So you have one which you train parallelly.
Huh.
But I guess like a lot of that, these two lectures had a lot of theory, but I guess when we start implementing them, then it will have a better, we'll get some better understanding of that. It's like a lot of theory thrown in these two lectures right now.
Yeah, it's good though. It's not that difficult. Everything is fairly reasonable, and we've seen pieces of this in other deep learning, but just not for this structure.
So then he talks about supervised and unsupervised thing. When in some of the cases, when you have just graph without an external labels, then how do you train on that? Then you use whole graph's internal structure you use that to basically train your graph. But right now, I'm not sure. I think I have not understood exactly in depth what he's talking about here. So I won't be able to comment on this. Anyone has any idea on this? Like, what does this mean when he is talking about this in detail a bit?
So basically, like it's a bit like when he was talking about the augmentation earlier. So, even if we don't have any labels, we already know properties about the graph. Like, for example, for nodes, you have degrees, page rank, score, cluster coefficients, etc. Then, you basically, like, for example, you can ask the graph to predict like the node information that you can extract by the means, or like if link prediction, you can like drop some of the links and ask the graph to predict whether link exists between various nodes. And then for graphs, you can kind of predict, as one of the example, like predict whether they're isomorphic, etc. And because these are like stuff we can get from just graph analysis itself, then you don't need any labels. So that's what they mean. It's a bit like training, like like what the language models where you already have information, you just kind of ask the network to predict, oh, what's the next word, what's the word around me, that sort of thing.
Or topic. It's just unsupervised, not labeled.
Yeah.
Okay, understood. Yeah. Okay, so yeah, so he talks about the final loss for regression. He sorry, for classification he talks about, I think, binary cross entropy. Yeah, sorry, cross entropy. So in the 10 case we can use binary cross entropy. For regression he talks about MSE, and I think that's then, yeah, then it's like basics, pretty basic stuff about it. Start talking about like in case of we have certain specific problem, we can use those metrics also, ROC, AUC,
Standard scoring.
yeah, pretty standard stuff there.
Okay, good. I mean, not easy necessarily, but just things we've seen before. Good.
Yeah, a lot of times. So okay, so how do we split our data set into trained validation set? So okay, so if we have multiple graphs, then we can split them into these training, validation, and test set. For graph, why it is special? Okay, so okay, I think I also need to go to it. But
so yeah, that's interesting. So subgraphs are going to be specific, like I assume if you have a big giant graph, you would want to break it up into subgraphs. And what's the mechanism for that breakup?
Just break the links. That's what he said here. Just break the links. Right.
But yeah, sorry.
So you have this. So in this case, he's got this big giant graph, right? 1 and 2 is something, 3 and 4 is something, 5 and 6 something. So what he said is, like, rather than have leakage, right? So because if you consider these as like, just a graph with these 2 nodes, but then you would have leakage from the training side, right? So let's say you consider only the test. Since it's connected to the training and the validation, there will be leakage of information. So basically, to create your data set, he said just break the links, across the graphs that you have selected, and proceed. Right? It'll work. Basically, it's.
Huh. That's it. Now, but the actual creating of the subgraphs, there has to be some mechanism for that. Like just given a graph of 100 nodes with 70 edges.
I think you find connected components or weakly connected components, and you just split the, cut through the places where they need to be cut.
Oh, you figure out like average number of nodes should be similar if you're trying to break it up into similar subgraphs.
Yeah, I think that you might take on faith. I don't know. I mean, I don't think there is anything.
Yeah, so what is said is like correct. He talks about breaking these links, but yeah, I have this question because like this whole graph structure is defined by these connections also. So if we break that, then it might affect like how do our GCN understands the graph.
Yeah. Well, I mean, if you look at regular machine learning, you have something called stratified sampling, but it's not always used, right? So in that sense, stratified sampling is a special case of sampling, basically, or the default is basically random sampling. So it's a luck of the draw anyway.
You're right. So it's random. It's not necessarily looking for the subgraphs to be similar in any way. It should be different in many ways to give it the expressiveness. No, this is a hard problem. This is interesting.
Yeah, but he also mentions that it should be only it is only applicable in node or edge prediction.
Oh,
not the graph task completely. So then is another is like when we have multiple graphs, then each split can be observed. The graph within the split, a successful model cannot generalize unseen graphs. Okay. Okay, this is something.
There you go. Oh, this is good. Yeah.
So it's okay. Just what is the difference between them? We can only observe the labels of their respective nodes. Okay, so we basically take like separate those labels, and we won't, I mean, those training set labels will be only visible while training, the others won't be.
Mm-hmm.
Okay. So that is transductive, where we are splitting the nodes. Okay, what was that then? This was a transit.
Yeah, transductive, you can see the structure, but you cannot see the labels, right? So that's not splitting yet. So basically, it's kind of a partial split, right? Because you can see the. I don't know how that will work though. I mean, because if you don't know the labels, or maybe you can see the features of your neighbors, right? So if you look at the blue one, right, that is the validation one, right? The validation one can see the features of the nodes in training because of the neighboring nodes that it has in training, but it cannot observe the labels. So it can get the features in when it pulls it for its own use, but it doesn't, it will not see the labels. Kind of lame though. I mean, I don't know. Yeah, we'll see. Yeah.
So you're
Yeah,
saying
I
like,
think they talk about that later, like you increasingly include more information as you go from training validation to test sets.
so basically these edges will exist, but from perspective of A, I won't be able to know whether it is coming from B, C, or any other node. So the label, I won't be able to know the labels, but
You won't be able to know the labels, but you will be able to see the features.
See the features, get the information from those.
That's
nodes.
fair. That sounds fair. Like it only informs it to the degree that it would, except for what it is.
Right. Exactly. Yeah.
Wow, that's interesting.
Okay, so the inductive one, basically these are independent graphs, but you also mentioned that only the inductive settings are well defined from graph classification. I guess they are also having that trouble, what we are having. So, okay, so the 5 graphs then divided into 3 parts. Now link prediction. Okay, I guess basically this is setting up. Okay, yeah. So I think there are this messaging edges and supervision edges I was talking about earlier. These like some difference between them. Maybe so. Supervision edges are basically used for computing objectives. I did not understand what is the difference between them. And messages are used for GNN message passing. Anyone has in like some idea about what does these 2 points mean here? What is the difference between them?
Supervision for predictions. No.
So after step 1, only message edges will remain in the graph. Supervision edges are used for supervision of edge, and prediction made by the model will not be fed to GN.
Or maybe it's because it's self-supervision. So these might be the kind of pseudo labels that, you've broken the link. Now you're trying to make it predict, right? So.
Okay, so what I understand is that all these edges will be there, and in whatever we are feeding in the graph, this 3, 4, I mean this label, so this edge 3, 4 won't be there, but we will tell them as a like out target vector, a target value that this value exists. So
learn to find it.
Yeah, so just find it. Okay,
yeah.
And
for scoring. Cool.
Okay, understood. Okay, so basically, so how do we choose the supervision edges? Is it like randomly chosen while doing this self-supervised learning part? I don't know, like whether you talked about that.
I think it's just random.
Okay.
Yeah, ideally, if you were to get too deterministic, you would impose something into the problem that you want to impose. There'd be a bias. You would be biased. It would have to be random.
Right. Okay. So that was I think for node. This is for edges, like how it's being done. So this is the training set. Then I have this validation and test set. But now in the training set, this 2.5 is already present. Won't okay? Okay, these are graphs, different graphs, I guess. Oh yeah, 3 graphs, 3 different graphs. Suppose we have a data set of 1 graph, then there is a problem there, transitive link prediction set. the entire graph is observed in all dataset splits. We need to hold our validations. Okay. Okay, so in this case, this is the actual graph structure, and we remove, I mean, we basically break all the training and validation and test edges. We use that for training, the test edges, so training edges, and then we try to use that to predict this validation and as well as test ones.
That's interesting. Much different than classic.
True.
It's similar to the master language modeling, right? I mean, you basically hide some words and make, and that's your labels. Basically, you train the model to predict the words that you hid. And then at inference time, you basically send in another sentence with some hidden words and you make it predict the hidden words.
It is, you're right.
Yeah.
But in this case, like we are using, if you say like we are using the same sentence again, right?
Yes.
So,
or similar sentences, right? So what happens is, let's say for, if you look at knowledge graph link prediction, you might have, so I'm oversimplifying, right? So you might have a disease and a symptom, and in your ontology, some human basically connected the disease and the symptom, saying that when you get this disease, you have this symptom, right? And so over time, these humans have connected many diseases and many symptoms, right? So now you encounter a new symptom, right? Which disease should it go with, right? So, and that's basically, the link prediction task based on the features associated with the symptom and the features associated with all the diseases that you have. It would try to, find feasible prediction links, right? So, yeah. So you can obviously do other more cooler things like terrorists and whatnot, right? So, yeah.
But in general, you're taking a big set of things that you have or defined, and you start taking pieces away just to assist in the learning process.
Yes.
Okay. Yeah. Total sense.
Okay. So I guess it's like repeating the same point again here. Setting up this thing. This is the summary. So okay, should we move to ninth chapter, lecture slides? If we
Not as well.
Okay.
Review there.
Yeah, it's pretty a lot of review thing. Setting up link prediction, I guess, till this thing. A lot of repetitions of this. Yeah, I guess this was the point. Training complex.
Back to that. Good. All right. Now we got implementation. Oh,
Yep.
That was it.
So it was GNN training pipeline. I guess Deep Snap provides core modules. I haven't looked into it. Even GraphGym, I haven't checked yet. Okay, I think now the lecture starts. So like if anyone has done this properly, I have just gone through it once. We want to maybe talk on this, then it would be good. I haven't done it much yet.
I've gone through it once as well, but again, so. Okay,
cool. So yeah, this is the same thing which we has been basically telling on structure of graphs, repetitions. So he talks about normal GNN. Yeah, then he talks, he stresses the maximally expressive GNN model. Basically, what does that mean? It means like basically to ability to distinguish between different graph structure. Now, so yeah, he talks about if I have the whole idea is that if I have a node and if it is getting information from multiple nodes, how do I distinguish that specific node and like based on whatever information I am getting? How do I pool that whole information into a single vector or a value, which can basically tell me, which can help me distinguish that from other node, which is getting information from other disconnected to different nodes, other nodes. Now, so he talks about the graph sage, which is max pool, and he gives this example that if yeah, I think it talked into last thing. Just a second. Okay, yeah. So he talks about this thing. So if I have this 2 and 5 nodes, they are getting information 1, 5 and 1, 2, 4. And in case if we are using the max pooling, for example, if I have 5 has the max value there and 2 has the max value there, and both are very similar, then in the end I'll end up with something which won't help me distinguish between 2 and 5, because they will have a similar final output. He goes, yeah. So he goes with a color example somewhere here. Yeah. Just a minute. Yeah. Yeah. This is the basic structure of this one node 1 and 2. So one is basically getting information 2 and 5, which is getting information from 1, 2 and 1, 2, 4. Similar way, if the 2 is getting information 1, 2, 4 and 5, same way. In the end, they have the color basically represents whatever the embedding tells you. So in this case, we are not able to, the GNN is not able to distinguish if the end final value, what I'm getting from after aggregating the information from different layer is equal on both sides. I won't be able to tell like if those two nodes are different. So he talks about injective relationship, that each like whatever output I am getting for each node, that should be unique. So in case 1 and 2 are both giving me embedding B, I won't be able to tell difference between these two. So that is the whole idea about the maximally what was the term I'm forgetting? Yeah, so the node embedding should be, sorry, yeah.
Maximum expressive.
Yeah, maximum expressive. So the node embedding should be injective in approach. This relationship should be embedding. This relationship should be injective there. That is the whole point there. So okay, further expressive with GNN feeds to limits. So the if like basically if my this node at each layer is basically able to keep the information from them, how much information I'm getting from them, that might be helpful in while aggregating, that might be helpful in making sure that this relationship between the embeddings and the nodes are injective. So driving home the same point again and again, basically giving some examples. And now he talks about so there are 2-3 ways he talks about like how the aggregation is done. So GCN uses mean pooling, GraphSage uses max pooling. So this is the failure case for GCN. If I have these two embeddings, if I call them 0 and 1, and if I call them call yellow as 0, orange as 0, and blue as 1, then on an average, both, if I take average of them, so they will give me the same value, and I won't be able to tell difference between them. And sorry, okay, GCN was mean pool and GraphSage is max pool. So yeah, so GraphSage is max pool, and if the maximum value of each, so if blue is the maximum value for each embedding, then again I won't be able to tell difference between them. So now the thing is that like, yeah, so expressive power of GNN can be characterized by that of neighbor aggregation function. So those two examples he gave, he basically tries them as an example to show that those are not exactly some ideal aggregation function. The neighbor aggregation is a function of multi-sets with repeating elements. GCN and GraphSage aggregation function fail to distinguish some basic multi-sets, so because, and hence they are not injective, so they are not maximally powerful GNNs. Okay, so then he talks about what kind of function will be most like how do you design such injective a function which is injective. So he talks about some nonlinear function which is which takes the summation of f of x, where x is basically in that the whatever information in that node. So f is applied on individual if it is the information is in terms of a vector, then maybe f is applied on each of those values, and we apply some sort of a nonlinear function on that. How do you define that nonlinear function? Yeah, he gives some proof on that. How do you define that nonlinear function? He says that we can use multi-layer perceptron. He quotes universal approximation theorem. So if I know that I can represent that relationship as in terms of a non-linear some injective function, that can be very well approximated by a neural network. Okay, so MLP hidden dimensionality of 100 to 500 is sufficient. I don't know where this is coming from, but I guess this is more on the heuristics and the number of experiments which have been done. What was this? Graph isoform network, apply an MLP element by sum followed by another MLP.
This is where he uses the summative thing, right? So the pooling is sum, not max, not mean. It's most expressive.
Okay. So this one you are talking about, right?
Yes.
So this is one MLP, and over which this is another MLP. This is this what it is he's talking about?
Yes, the F is one MLP and the phi is one MLP. Yeah.
So okay, MLP is a framework in which there are two functions, F and phi.
Yes.
Correct? Okay, good. So yeah, I think this is apply an MLP element-wise sum followed by another MLP. Okay, MLP function.
Yeah.
So GIN neighbor aggregation function is injective. There is no failure cases. No for okay. So now we describe the full model of GIN by relating with WL graph kernel. I think it was he talks about the graph we used for coloring those individual nodes, which was based on taking the hash of the concatenation of the current value of that specific node and concatenating with the values of the neighboring nodes and taking a hash of that.
Right.
So he mentioned, yeah, sorry.
Sorry, go ahead.
So yeah, he mentions that after k layer of color separation, we basically keep on doing it till it basically stabilizes. I think that was one question we had in our second session, and he has said that we keep on doing it till this values become stable over time. So this is also some sort of a injective function there, because individual hashes values are separate for each other. Now, yeah, so this will help us in identifying whether two graphs are similar or not. Two graphs are considered isomorphic if they have same set of colors, color being the hash output of individual nodes. Am I correct here?
Yes.
Yeah. Okay. So yeah, so GIN uses a neural network to model the injective hash function. Specifically, we will model the injective function over the tuple root node features and neighboring node colors. Okay. I don't understand this.
The same exact set, the same exact. Yeah, that might. So the morphism is expressed in the color in the hash, the unique hash of the coloring, and so two graphs that have the same exact set of hashes are isomorphic.
Exactly.
Okay.
And here, this is basically an attempt to bring, the message passing framework and the neural net framework together, right? You're saying, the WL is basically a message passing framework, right? You basically look at your neighbors, collect their hashes, and create, accommodate in your own self. However, there is like a lot of analogy between the two. The formulas look the same and everything. So in that sense, it's kind of an attempt to bring these two ideas together.
I see.
So we are using this neural network to approximate this hash function. Right?
Exactly. Yeah.
Okay. So in any injective function over the tuple, this one, okay, this is the same tuple as this.
Yes.
So like
And-
root node and the neighboring node.
And in
Feature.
some ways, if you think about early work in computer vision, right, people used to come out with edge filters and blur filters and so on, right?
Right.
Basically by, creating by hand convolution matrices, right? Whereas, with CNNs, you basically learn those convolution matrices given your objective, right? So it's the same, here you're trying to learn a hash function,
Right.
which is grounded in theory, but, using data, right? Using neural networks.
Right. Instead of deriving that.
Exactly. Right.
Okay. Yeah. So that can be modeled as this. So this is basically the root, and this is the neighbors. The U is roots and V is the neighbor. So we'll be taking a weighted sum of them. Okay, this is also a learnable scalar. Okay, I didn't know that. The input feature is represented as a one hot direct summation injective. I guess I am lost a bit there. So yeah. What is the relation between this and these two?
So you have here is basically a weighted sum of features from each node, right? So that's your inside part, right? The where you have let's see. Well, inside the GCN part, he's kind of not making a distinction between. So in the example thing with the the blobs, there is no distinction between the nodes, the current node and its neighbors. They're all a bunch of nodes, right? Here he is making a distinction.
And also he talks about like we are learning this this parameter to epsilon.
Yes.
So
how much to weigh yourself compared to your neighbors?
So we'll be training the neural net as well as this epsilon parameter for this epsilon parameter too.
The neural net will contain this epsilon parameter. So if you learn the neural net, you will learn the epsilon parameter.
Yeah. Okay. So GI model basically, okay, repeating the same thing. He corrects. So differentiable color has hash function. Okay, this is the way he talks about like how do you loop over it, and there's a difference between them. DL low dimension the hash conversion function. Okay, the comparison between the WL graph and GIL as you're talking about sometime before. So what is the advantages? Node embeddings are low dimensional and they can capture the fine-grained similarity of the different nodes. Parameters on bit function can be learned from downstream tasks. Okay, generally this is exactly same. So how do you measure the expressiveness? Like I don't think he talks about that. Like how does this know like what is the expressiveness of that?
I think it's proof by negation kind of thing, where you bring up these examples where each of these the GCN and the Sage graph Sage fails, right? And you show that GIN does not fail at either of them. So therefore, GIN is the most the best, right? So I think it's kind of a proof by negation. You cannot prove conclusively beyond doubt that it is superior for everything, but across these examples, it seems to be.
Yeah, so maybe some sort of a like task where they have to focus on node level structure details. In those cases, it might be able to. It would perform better than those graph Sage and GCN.
Right.
Okay, the power of pooling. Yeah, that is the same repetition of the what was mentioned before. Mean and max failed, max fails, mean and max both failed. Like my discrimination power. Okay, yeah. So now he talks about like including the cycles into that to increase the expressive power of GNNs, and that I think would be of something we might be learning in the future lectures.
Okay. Wow, that was great. I didn't think we'd get through that.
No, I think this was 8th and 9th was to be covered today, so I thought I'll just go through it fast.
No, it's good because I have to basically just watch stuff this week and work on Colab 2 And then we got
Yeah.
a week, which is good.
I'll
Okay.
try to work on Colab too. I think we have this a bit relaxed week, this thing. So because only one lecture has to be covered, so I'll try to finish this Colab too, and we can have some sort of a discussion.
I can tell that that's going to be enough of work for me. I'm kind of sad that the homeworks are just off base. They're just totally out there in a place that I can't go.
So homework 2 is actually a lot more relevant. Like homework 1, just a lot of like just more traditional graph stuff which isn't covered in the lectures. So I think kind of for homework 1, I might go back again after I finish the rest and just get the basics. But it's like homework 2, you'll find that there's a lot more relatable.
Okay, that's good. I just don't have literally the time to probably do that. Although I don't want to stop other people from doing it in any respect. I know David keeps asking a little bit about it, and I feel bad that not necessarily hitting a lot. But I mean, just hitting the lectures itself is kind of the core aspect of the course. So I'm glad we're staying on that very well.
Yeah, homework 1, you can actually subvert some of the questions. So I'm never going to do the, well, not never, maybe, proofs. I basically want to know how to use these things, right? So I looked at question 4, and it's a bunch of proofs, right? So what I figured I'll do with that is basically try to take the real graph from question 1, right? It's a download from Snap, and try to do spectral classification on it, right? So I did some work there. I still need to, I learned about the Fiedler vector, which is used to partition the graph and so forth. So there's, so if you kind of dig from an applied kind of standpoint, I think these are good high level ideas that, one should know, not necessarily from the math end, but, at least from the applications end. And doing these exercises by subverting them into kind of an application-oriented thing helps to solidify your concepts as well, better than actually doing the course, just watching the lectures.
Agreed. I'm just trying to make sure that I wouldn't want to go down a rabbit hole on a homework at the expense of 4 or 5 lectures.
Yes, of course. Yeah.
And I'm just slow working through these. But. Okay, that's good. Thanks a lot. Have a good week, and we'll continue kind of poking around in the Slack channel, especially now that we kind of got I think we have a pretty good handle on Colab too. I'm going to revisit that and try to implement, with Wendy's help, how she teased that apart. So.
All right, guys. Talk later.
Okay.
Thank you. Bye.
Bye. Thanks,
Bye.
Nicholas.
Have a
Yeah,
Bye. Thank you.
Bye-bye. Have a good week.